So, hi everyone, welcome back to Liverpool. So, we're starting off our 2025 lectures with Ioana Ciucă, who's newly of Stanford University and will be talking to us today about democratizing science in the era of agentic AI. So, when you're ready, if you'd like to share your slides and get started.
Thank you so much, Alex, and thank you so much to the committee for inviting me to be here with you today virtually. I'm really excited to give a talk about my work in AI. I got the read. First of all, can you see my slides?
Yeah, looks good.
All right, perfect. So I got rid of Agentic AI because I realized the time was a bit short, and I just in the end decided to talk about our work at UniverseTBD of democratizing science in the era of AI. And then hopefully if you invite me next year, I'll tell you more about agentic AI because 2025 is proving to be a very decisive year in this space. So just want to say that today I'm talking on behalf of our team. This is truly a team effort, and hope that you like the work that we're doing. So just a brief outline of my talk to guide your attention. First of all, I'll introduce who we are, why we're doing the work that we're doing, and how we go about it. Then I'll deep dive very briefly into a brief history of large language models. This brief history covers the last 10 years. This is a very long history, over 70 years, 78 years, but the last 10 years have been really instrumental with the advance of compute. Enabling these methodologies to come to life. Then I will pretty much talk about how large language models can assist astronomy. Now that they're here, can we use them in a useful way? What do astronomers really want them to do, and now and in the future? And then I'll provide two concrete projects that we've been working on. The first one is Pathfinder, led by my wonderful colleague and co-founder Karthikeya from Columbia. And the last one that I'll talk today about is HypoGen, which stands for hypothesis generation. And this project is more sort of experimental at the moment. We're exploring quite a few avenues, and our goal is to introduce HypoGen to Pathfinder and release it to the community as a module to inspire researchers to ideate with AI. And my last slide will be a very philosophical slide that sort of provides stepping stones into the future and where do we see this future going with AI for science. So we are a team that was founded in April 2023. This was around the same time of ChatGPT. My co-founder Karthikeya and I sat in a coffee shop in America, and we decided we had to do something about it. About, like letting the community know what's happening in the AI for science space. And we came up with UniverseTBD. Originally, the name was to be changed. So we placed TBD as a placeholder. But in the end, it kind of got an identity of its own. And I guess it encompasses the thing, the sort of the realization that everything is changing. And we really are feeling quite empowered in that now. We were originally very few of us. We were like maybe 5 people. Over the last 2 years and a half, 2 years, we've grown into a 30+ sort of human beings effort, volunteering their time. The interesting thing about our team is that we are fully remote and we are spanning 4 continents. We are astronomers, of course, software engineers, computer scientists, and also we even have an artist in residence. So this is truly a multidisciplinary team that makes our meetings happen, even though it's very hard to find a good time to meet. Our mission is crystal clear. We want to democratize science for everyone, and we want to talk to our community to understand how to best do this. We are thinking the best way to achieve our mission is through a vision that empowers people to explore, synthesize, or even create new knowledge with artificial intelligence. I come from a background where I didn't think it was possible for me to do astronomy. And then when I started using machines, I realized this can be done. And I think both Karthikeya and I feel very deeply about this. So how can AI be a tool that empowers and augments humans in being bold and taking risky projects on and not be afraid to sort of working on very high risk projects that otherwise they wouldn't take without AI. And I think one thing I really want to mention is that what kept us going over to the last 2 years through our, joys and tribulations was the fact that we have very strong values, and we came up with these values ourselves. We asked the team, and we deeply value openness. So everything that we do has to be open, excellence with purpose, experimentation, junior empowerment and leadership. Our executive team is made by 7 people, and a few of us are very quite junior. Maya, who is our deputy lead, is a PhD researcher. Of course, we also care deeply about integrity and transparency. And I think we also want to make our team work to show the community that it's possible to do this and base our efforts on values. All right, so now that I told you a bit about our team, we said that we want to democratize science for everyone, but why do we want to start with astronomy? Apart from the fact that most of us are astronomers and really love astronomy, there are a few important reasons why astronomy is a good place to start. First of all, astronomical data is relatively harmless. Astronomy is open. We have open software, we have open papers, we have observed data that's pretty open. Astronomy is not profit-driven, so our incentives differ quite a bit from other other efforts that may want to prioritize profit over something else. In astronomy, and same as research, we really care about the pursuit of knowledge at the very core in an idealistic world. And of course, astronomy is community. What makes our science so great is our community. And we really want to learn from each other and to work with each other and ask the biggest questions. So these are some of the reasons why astronomy is a great place to start, apart from also the fact that we have a lot of data. So this is also a bit about, I want to show you a bit about us. A part of our team here was the European Space Agency, before Space Science Workshop organized by our exec, Dr. Sandor Kruk. And yeah, we are very excited and very happy to be here. And just more is more of our team at the moment. I just want to give a huge shout out to Maya and Pranav for our junior executives, and they are really absolutely killing it. So we're very happy to have them in our team. All right, so I told you a bit about the mission, why we want to start with astronomy, but now I also want to provide some motivation why we really care about AI and how AI can help astronomy. So Dr. Alan Turing in 1950, I think around this time he was at Manchester University. He came up with this, he wrote this paper, Computing Machinery and Intelligence. In the very first sentence of this paper, he poses this question, can machines think? He then goes on and says we need to reframe this question into something that we can make sense of, and he proposes the imitation game, also later known as the Turing test, where you have a machine and a human interacting via typed text, and then you also have a judge, and it is said that if the judge cannot discern which is the machine and which is the human, it is said that the machine has passed the Turing test. I think with AI and with large language models, I see now a trend where we focus so much on the recent development that we forget, the pioneers of this field. And I think Dr. Alan Turing is a true inspiration, and it's great to follow in his idea to answer this question, can machines think? Over the last 10 years, there has been a boom of knowledge. Just looking at archive papers, there are so many papers in computer science, and it's very hard to keep track. So I think for audiences where I speak, I try to give a sense of the last 10 years and the seminal papers in the field, and use that as a starting point for further exploration. So the way I see things is that we have attention, which is a mechanism that allows, for example, that allows us to connect parts of a sentence to what's going to follow afterwards, which parts of the sentence are more relevant in predicting the next word. Then we have the transformer model that uses this attention mechanism without convolutions or recurrency, which actually allows this to be done much more efficiently. Of course, what happens once you have the transformer model, then if you keep, making bigger transformer models and training them for longer on bigger data sets, they get better. But to do that, you need to have a lot of GPUs, or you need to have very efficient training strategies. So a lot of this expansion was enabled by the fact that NVIDIA brought up the GPU revolution. Of course, humans are very much needed. Once you have the models, you scale up the models, you train them, they're still not performing quite as well. So you do need the humans to align these models so they perform very good on some tasks. And the papers that really enabled this work are as follows. So 2014, Dimitri Bachtanau comes with this paper, Neural Machine Translation, where he proposes the attention mechanism. Transformer takes this and scales it up to a transformer model. It's an innovative way. This is the first time we're not using recurrent neural networks for this task of predicting the next token in a sentence. Then we have the first BERT model, 2018. The folks at Google trained this large language model called BERT. Then as time goes on, pretty much this field branches out into open source and closed source models. You have here on the right, you have this sort of branching with GPT-3. These are closed model now developed by frontier labs like OpenAI and Anthropic. OpenAI in 2022 comes up with this paper, InstructGPT, where they pretty much said, hey, we have trained this large language model, but we don't really think it's what we want. So they use the humans with reinforcement learning to pretty much tell the model, this is the behavior we expect. Let's align it to this behavior. And the humans are used as a sort of a mechanism to drive this alignment. This is 2022, 2023. So 2023 to 2025, there has been a boom of expansion. We scale things up. We change some training strategies. We change some inference strategies as well. And now some of the new models are absolutely, we are running out of benchmarks to test the capability of these models. So, but I hope this is a helpful slide to kind of give you a flavor of what's been happening in this space. All right. So over this period of 2017, when Vaswani et al. Came up with the transformer, and 2021, when OpenAI released GPT-3, this model size and computation have increased exponentially. At this point, you might wonder why. Why do we really want to train these large language models for longer? The reason is that larger models seem to require fewer samples to reach the same performance. So what I'm showing you here in this plot, on the x-axis, you have the tokens process. So this is pretty much the text, the amount of text that these large language models are trained on. And on the y-axis, you have the test loss. And what you can see is that the bigger model achieves a lower loss at the same tokens processed. So in a sense, the bigger they are, the better they are, as quantified by some loss function. They also seem to be more capable of generalizing to various downstream tasks. So for example, when I mean a downstream task, I mean like question answering, summarization, translation. So here in this plot, I'm showing you on the x-axis the number of parameters of these large language models. We're talking about the billion level parameter models. And on the y-axis, you have accuracy. And you can see that the bigger models have a higher accuracy across the three regimes of zero shot, one shot, few shot. One shot means that the model sees one example. Few shot means that the model sees multiple examples. Zero shot is just the base model that hasn't been given any example to solve that particular task. I can't remember exactly what downstream tasks they used to get this plot, but it's probably Q&A or relevant NLP tasks. All right. And here in this plot, I'm showing you sort of how these sort of emerging capabilities across the downstream task change. depending on the value and depending on the number of the parameters of the model. So you can see a 60 billion, we're doing very well, I don't know, Q&A, and then it gets better with translation. And then as it gets bigger and bigger, we start seeing more reasoning heavy tasks being completed by the model. All right, so now that we have a bit of a setting the scene with the large language models, we know they're the bigger they get, the easier they can adapt to downstream tasks. So we know they're powerful. How can these machines assist science? And this question is a very important question philosophically as well as scientifically for us. And I found in this paper by Cranetol 3 different ways to think about it. So machines can act as a computational microscope, and we are very used to this. So this is where the machine creates new data. You can think of a large computer simulation. And then the human scientist uses the data and extracts insight from it. And we do our nice plots and we really nice analysis, and we share it with the community. The second way machines can assist science is as a resource of inspiration, where pretty much you can think about here as like explorative literature search, where the machine explicitly looks for surprising or interesting new ideas or unexpected connections. And then the human expert looks at those connections and says, yeah, this is great. This inspires me to pursue this further. And the last frontier, which has been hypothesized when the paper came in 2022, and now I think we're getting closer and closer to the moment, is machines as an agent of understanding, where the AI obtains and explains concepts to a human in a way that is indistinguishable from a human expert. So this is sort of, you can think about the Turing test with a spin. And my personal view is that we're not there yet, but we're getting closer and closer to something that resembles an agent of understanding. All right, and now the fun bit. I think you really like this part. So a few folks and I think this effort is truly led by Dr. John Wu from Johns Hopkins. He really put all the team together and brought us all together. We really wanted to answer this question: can large language models be a useful resource for astronomy? And we tried to do things in a principled way. First of all, we set up the team. John brought us all together, brought astronomers and human-computer interactions experts together at Johns Hopkins for a summer. We brought some brilliant young researchers with us. And pretty much what we try to do is we have this group of astronomers at STSCI. Let's enable them to interact with the chatbot, that's LLM-driven chatbot, and see what they ask the chatbot, see what kind of queries they ask, see how they interact with this chatbot. And then what we did is we used 35 experts, and then they provided around 350 queries. And then we looked at them and we spent a month trying to categorize them in a meaningful way, led by Prof. Anjali Field. She really helped us get this job done properly. And once we did that, what we did afterwards, we actually went to and asked 10 astronomers. We interviewed them in depth to understand more about their interaction with the system. And I really am curious to see what you think about this, because I have not seen a study like this done before, and it's exciting to see what the community thinks about it. So just a bit of a sort of summary here. We had 37 astronomers, and we got in total 378 queries. We had emojis, we had feedback, and so on. And here is sort of a very simple idea of how the system works. We built a chatbot. We allowed the chatbot to exist in a Slack space, and then people could just ask this Slack app question. And then depending on the answer, you could thumbs it up or thumbs it down, and people can comment underneath the chatbot. One disclaimer here is that you can only ask one question to the chatbot. You cannot actually have a conversation. This is something that we're thinking about for the future. And once we had 378 queries, the hard job started then, because we actually had to look at all of them and try to put them in some meaningful grouping. And these are the type here, what I'm trying to show you is the type of questions that people came up with, like expert astronomers, professional astronomers came up with. And they span around 9 different categories. So first of all, most people are really interested in knowledge-seeking specific factual. They were trying to ask questions like, for example, what is the most massive known spiral galaxy in the universe? This is very specific question. Secondly, people really cared about deep knowledge. They wanted to use the system to answer questions like, what are the most promising subfields for now? Of course, people really cared about bibliometric search. We really want to find recent papers or papers that are useful for our studies. We also wanted to have a broad description or common sense. For example, this is more like not necessarily specific factual, but a bit broader than that. What physical characteristics indicate the transition between a brown dwarf and a low mass star, for example. And my favorite kind of questions were the ones where our experts were asking stress testing questions, where these are questions that are unrelated to astronomy, but yeah, the humans really want to cheat the system, see what the system can do, what's it good at. Then we also had both capabilities. In this way, they don't want to cheat the system, but they just want to understand from the system what kind of functionality does it have. All right. And the last 3, knowledge-seeking procedure. These are very relevant to things like, what method did this paper use to solve this question? Bibliometric search, looking for a specific paper or author. And again, one of my favorites are the unresolved topics. These are the questions that really don't have a definitive answer. And my hope is that the AI can help us get a definitive answer. But you can also think about these questions as really a frontier type question for this AI system, as they're very hard to solve. All right. And then we did a bit of, once we categorized 378 questions, we looked at their distribution, and we found out that people really asked a lot of knowledge-seeking specific factuals, so lots about facts, and then deep knowledge was also very sought after. Of course, then followed by bibliometric search. So we really want the facts, or we really want the deep knowledge, and then we want to sort of secure our knowledge. I mean, know what exactly the bibliometric resources are. So to me, this was no surprise, and this doesn't vary very much by gender, because we also have access to the gender and the age of our users. So here I'm just showing you that there's not much different by gender for categories. There's a slight difference in bibliometric search, but everything, and unresolved topics, with women tending to ask more unresolved topic questions. We did not have very many, so this might not be statistically significant, but it's an interesting pattern to look at. One pattern that both Josh Peak and I, who was also part of our wonderful team, and he really inspired us to ask these questions, was that if you look at the distribution of thumbs up, the number of thumbs up and thumbs down per category, so for example, per age category, you want to see if a certain age group asks more thumbs up or thumbs down. And we see this very interesting trend that the early career researchers tend to thumbs up the system a lot more, whereas the more experienced folks who have spent a bit of time, have seen the flow of like ups and downs in astronomy, tend to be more harder to impress. So they tend to thumbs down the system a lot more in a more significant way. So for us, this was a very interesting trend. We really enjoyed seeing it. All right, so now before I go into more technical details about Pathfinder, before we build Pathfinder, we really wanted to understand, okay, cool, these are the type of questions, these are the type of questions, this is how often they get asked. But what do researchers really want from a system like this? And this knowledge we can only get by interviewing people and learning from them. So we did that with 10 people, and most of the time, people really wanted to have a confidence statement. When a chatbot provides an answer, we want to have an idea about how uncertain it is about that answer, or provide some form of limitation statement. People really cared about graceful refusal. This is a very human, I think, a very human result. Yeah, we don't want to be told, I don't want to answer your question, apparently. People really want comprehensive and complete answers. They don't want any essential information being left out. They want a filtering of irrelevant papers when providing that answer. Consensus evaluation, we really cared about consensus, and this kept coming across our experiments. Consensus is really important. No harm or misleading information. And we also want systems that reduce biases in research. So for example, if you have a paper coming from a very well-resourced institution, and this paper being quantified by large number of citation, but then if you have a paper from a smaller institution that doesn't get the same visibility, yet the science is very high quality in both cases, we really want to also retrieve the second paper. A system like this, we want to shine the light on the papers that really are good and advance science forward. So people really cared about this sort of more technical dimension, more ethical dimension as well. All right, so armed, equipped with all of this sort of knowledge about what kind of questions people want to ask, what do they care about from these systems, about the system. Dr. Kartikeya, my co-founder, he really spearheaded this effort with Pathfinder, and the folks at UniverseTBD and Johns Hopkins, we really were there to support him. And he came up with this tool called Pathfinder, which is LLM-enabled literature search. Is available online. I'm not sure if peeps have used it. It's a really good tool because it's really grounded in human-computer interaction research. It's not just another chatbot. We really thought about how to design it properly. It's doing semantic literature search in astronomy, uses natural language to explore over 350,000 papers. These are published papers over some period of time. I think the last cut out was 2023. And then we combine advanced retrieval techniques with large language model synthesis. So the system is built in such a way where we really focus on the retrieval part. We care about the papers that are most relevant to answering a particular question. And then we use a large language model to sort of use that information and provide the answer. So the LLM comes at the generation part, but the retrieval part is very important for Pathfinder. And of course, the aims of Pathfinder are, of course, to accelerate astronomy research by enhancing literature review and knowledge discovery. The system allows us to ask questions in different languages. You can ask to explain concepts in a simpler way, in a more complex way. So it allows this adaptability as well, which I think democratizes science. And it's very much aligned with our mission. All right, so what we did, I think, with Pathfinder, we have the paper, ER et al. 2024 has been accepted now. The system is very elegant in nature, so it consists of the user asking a question. Then we have a metadata filtering system that looks at, filtering by keywords, filtering by date. We want to care about the more recent papers or not, and also filters by citation. And these modules are optional, so you can plug and play whichever you care more about. And then we use the system to, from these papers, we needed to transform them in vectors. So we use the system to a large language embedding model to get vectors from these papers, because vectors can be compared. And then we compared which vectors are more similar to the vector of our question. And then we brought those into the context of the large language model. And at the generation step, the large language model sees these papers, sees this information, and it formulates an answer. The entire framework is open source because we believe in open science. So the Pathfinder corpus can be easily downloaded I think the instructions are in the paper. We have also the data, the code is, I'm writing the testing code for the Pathfinder, and we're hoping to release 2 versions to the community. One that's the official version, and also the version that's now we're trying to also include HypoGen to the Pathfinder modules. So we're working on it, we're actively working on it. And now we host the app at pfdr.app. And how does it really work? It's very simple. You can ask a question here. Where are the oldest? I'm very slow type. I type extremely slowly in our galaxy. So you can ask that question and you go and do run pfdr. And then Karthik has a very metaphorical way of looking for the answer, making the large language talk to the papers, generating consensus. We have a module in the framework that cares about generating this consensus. You look at the date when the papers were published. I think our corpus was 2024, not 2023. And then you look at the title of those papers, you can go and investigate them. And then you get the answer from the large language model. And then there's also this consensus part where, we say across all the papers that we've seen, this is the consensus. And then we also have this very nice map where you can see that where the retrieved papers lie in the embedding space of all the papers, projected in a 2D map using UMap. So PFDR is Pathfinder is very simple to use, but it's a really, I think, a well-informed tool. We are not software developers, we're astronomers, so we built it for astronomers, and we're currently looking for funding to be able to hire people to allow us to scale it up and make it more available to our community. But it's available online and open. All right. So one other thing with Pathfinder is that we can use the embedding of these papers to visualize astronomy papers in a 2D map. We can cluster papers by semantic similarity. So if the vectors are very similar, come together, not just keywords, keywords in the abstracts and so on. And then we can also use these embeddings to identify links between subfields and, of course, emerging ideas. Where is the potential to sort of meet 2 ideas? I think this is to connect 2 ideas in this map. And this is the very nice sort of map that Karthik did, where you have these sort of mountains of star formation, galaxy formation and evolution, black holes. The Milky Way is somewhere in there. It's a smaller mountain, but it's there. And of course, you have these valleys where there's, where things are waiting to happen as quantified by the embedding in our text. Yep. And one thing you could do, and this is something that we've been thinking about, is we could see what's been happening over the last 50 years in astronomy, which are the new fields of science. All right. So in the last 10 minutes of my talk, I would like to talk a bit about hypothesis generation and how hypothesis generation falls very nicely into this sort of second way to where machines can assist science via resource of inspiration towards agent of understanding. So we're sort of between these 2 worlds. So at the moment, I think we are really still in resource of inspiration. But to see if we can get to agents, an agent of understanding, we need to answer this question: can large language models come up with novel and robust scientific hypotheses? And to answer this question, in 2023, when GPT-4 first arrived, a few folks and I really did a very small scale experiment where we took GPT-4 and gave it access to some papers and said, hey, come up with some ideas by looking at these papers. And then we had a very sort of simple evaluation strategy. 1 means it's really bad, 5 is impressive, and 3 is feasible idea. And we used human evaluation to get these scores. So here, what I'm showing you on the x-axis is the number of papers, y-axis is the evaluation score. And number of papers means that the model has access to a corpus of 100 papers to retrieve ideas from versus 1,000 papers to retrieve ideas from. And you can see here that across the number of papers, although this is a very small, like this statistically needs to be improved, of course, but as an idea, I think this is something that could be, we can learn something from this idea. You can see that the distribution of scores is very low. We're peaking around 2 point something, 2.5. So this is not, that's not even feasible. But what we did, then we took another model and said, hey, criticize the first model's idea and then regenerate my hypothesis. And then once we did that, we see this sort of trend where the feedback from the critique model improves the quality of the generated idea. And this was in 2003, and now there's research in 2004, 2005 that supports this view. So we are very excited to see that our experiment worked. And then the same happens for critiques. So if you look at the quality of critiques rather than the generated ideas, it seems that having feedback provided to the critique also improves the quality of the critique. Right. So then the team at UniverseTBD, we have wonderful junior researcher, Charlie O'Neill. He's been snagged to go to Oxford now. So he's starting a CS PhD in Oxford. He was from the Australian National University where I was previously. And we were, it's been a pleasure to work with him. And Charlie is spearheading this effort called HypoGen, and he's being supported by Tirthankar Gosal from Oak Ridge National Lab, Dr. Tirthankar Gosal, who's been extremely supportive as well with our GPUs and a lot of advice and knowledge about hypothesis generation, and Dr. Roberta Reilano, who's a world expert in reinforcement learning, works at Meta at the moment. And Charlie and the team, of course, the team is a team project, so everyone is supporting the project. The objective here was like, all right, we need to move beyond my small scale experiment with 100 papers. We need to move bigger. We need to actually come up with a benchmark data set where we can evaluate if these models actually come up with good ideas or not. Because Charlie comes from a CS background, we initially worried more about CS papers, but now we're expanding to astronomy papers as well. And the approach is to really try to look at the best papers in the field, the best by quantified by some measure, for example, being accepted to top journals and so on to top conferences. For astronomy is a bit different because we don't have this conferences system. And then we try to take all of these papers and structure them in a meaningful way. You can think about taking an abstract of a paper and formulating that abstract in a way that's meaningful. So for example, extracting the bit, for example, the problem that people are trying to solve, and the flip, which is the solution. And the question is, can you generate the bit, given the bit, what is the flip? And then we use GPT-4 and GPT-4o models for high quality extraction. So we are structuring these abstracts in this way. And then once we have the benchmark data set built, what we do is also we build a method to generate hypotheses. And I will not go into too much detail, but the method originally is built to optimize for 3 things. We want fidelity, we want novelty, and we want creativity. And we achieve these things using different ways. So for example, creativity, you can think about having these models that are generating hypotheses competing in a tournament sort of style. Novelty, you can think about having a critic actually criticizing your idea, and fidelity, you can compare it to the papers in the literature. And I would really encourage to invite Charlie to give you a very nice presentation about this, because it's a lot of work, but I'll try to show you very briefly what we try to do. So in order to see how HypoGen, the method, compares with other methods, like other models, on our benchmark data set, we had to devise an evaluation strategy. And here, what I'm showing you here is that, for example, if you have 2 systems competing against each other, B versus A, and you have 100 ideas generated by both, and the human judge picks which one is better. And then in those 100 trials, how many times did system B win? And that's the red rectangle. And then, for example, here, system B versus system C, how many times did system B win versus against the system C? And that's the red rectangle. And of course, if let's say red is bigger than blue, then system B wins against system A, and system B wins against system C. So what we did then, we took a smaller model like Llama 3, 8 billion. So 8 billion is a very small model. GPT, the current GPT models are trillions of parameters. So we're comparing a very tiny model to a very big model. And what we did, we fine-tuned the Llama 3AB on the structured data set that we extracted. We used a part of that data set for pure evaluation purposes, but we also used a big chunk of it for fine-tuning these models. So teaching these models how to come up with ideas. And then when we looked at the results, we were a bit sad, of course, because when we use a large language model judge, as well as when we use a human judge, we're seeming to get this sort of result that HypoGen loses against real hypotheses. So yeah, so I think in 34% of the times, HypoGen wins, as shown by this plot here. So 66% of the times it loses against humans. And this is a good result. I'm actually happy with this. But right now we are running new experiments and we have an improved methodology, and we're hoping to see if we can move this number up and sort of have a way forward for hypothesis generation. And our work is not really the only work. Of course, there's so many great works, and I think many people across the world are across the CS world and the NLP world are asking these questions. But research ideation is very tricky as a problem. It's very expensive and tough to evaluate because you need human experts to evaluate. You cannot really trust large language models to evaluate. And for example, this paper from my colleagues here at Stanford, they actually took 1 year to answer this question: can large language models generate novel research ideas in NLP, in computer science? And they got over 100 researchers and asked some of those researchers to come up with ideas. And they also had an AI system that came up with ideas, and they saw, in a similar vein to what we did, they saw how many times the human evaluators preferred the human versus the AI across different criteria. And what we see here is that novelty seems to be, and yeah, so here I have human versus AI plus re-rank. So AI plus re-rank means that the LLM came up with the idea, but there was a human expert that ranked the best ideas. So in a sense, there's the human touch there. And what we see here is that as evaluated by this score, and that score is from 1 to 10, large language model generated ideas with human re-rank are better than the human idea, are more novel than the human ideas, not better, no, but are more novel than the human ideas, and they're more exciting as well in computer science, in this particular topic that they used in computer science. Not as feasible and not many differences across effectiveness and overall. Overall, they say that the AI plus re-rank outweighs humans. So this is a really, I think, a really good study. They've done things extremely carefully. And I think it'll be interesting to see how this also applies to our field of study, astronomy, because astronomy is empirical, is a different kind of beast as a field. So it'll be very interesting to see how it works. And this is something that we're actively working also now with Prof. Mark Huerta's company. We're working on a project now to see how this works for astronomy. All right, and I guess for my last slide, and I'm running a few seconds late, but why do we, with HypoGen, we want to put the HypoGen model inside Pathfinder, but we don't get very good results yet. We know that they can be achieved because of the work of other folks in computer science. And why do we still want to do this work? Why do we persevere? And I think that's the last slide, it's a philosophical slide. Dr. Demis Hassabis from DeepMind, recent Nobel laureate, when he gave the Nobel laureate talk, I actually watched it from the very start to the very end, and I was very happy to see that his last slide was about astronomy, and the last slide was saying that AGI is the ultimate general purpose tool to help us understand the universe. And I think this is the right framing. This AI tool, AGI tool, whatever we decide to call these very powerful AI models in the future, is a tool. It will not take away the dignity and the joy of our work, but how can we use this tool to answer these very big questions is active work. And I really am excited to learn more from the audience here and also see what your thoughts are on this question. Thank you very much. And thank you, Alex and Andrea, for having me here. Thank you.
Thank you. Have we got any questions from people in the room? Yep, Katie.
So I was thinking, I think in your earlier slides, when you were trying to categorize the different questions, when the different people were trying to test the model. So I could be completely wrong or misunderstood everything. Would you expect a different distribution if you weren't getting them to test the model? So say if they were just, talking to the model in a general sense, do you think it would come up with a different distribution? What I mean is, say for example, would they be as likely to do that? I think there was an option for like testing the model, like really trying to see like what the model could, what you can make the model do. Would you expect to see that if they just thought they were talking to it on a normal casual day, as opposed to in this environment where you're more like just testing the model? Yeah.
That's a great question. I wish we had more time to explore this, to explore on how to answer this question, but I think I can give you some insight from our different experiment we had, which was these questions were asked in a public forum. This was the public Slack channel. And we saw that anecdotally, when we talked to the researchers, we found a very interesting trend that when they were asking the model questions in private rather than in public, because they could also ask the Slack chat bot in DMs. They would tend to ask more questions they perceived as silly questions in the Slack DM, and more serious questions in the actual Slack channel. So I do, just based on this anecdotal observation, I do think that, yes, the distribution would change if we just observed astronomers in the wild interacting with these instances without being, without being in a testing environment. How much they would change is a great question to explore. Maybe we can answer that question in the future. I do think that based on my interaction with these models, I usually ask them a lot more procedural questions, so coding questions. How do I code this? Versus more, I don't think I ask them as much specific factual questions as I do procedural questions. So it also probably changes with where you are in your career as well. I think the earlier you are, you probably want to make sure that what you say is right. So you might ask more deeper questions or consensus questions. But yeah, this is a wonderful question. And I think hopefully we'll answer this question maybe in one of our next iterations of the project if it happens. Thank you.
Thank you for answering that. That's really
Any more questions in the room? Yep, Andrea.
Yeah, about this, thank you for the talk, it was very interesting. About this project you're talking about, you showed this correlation, and basically more experienced researchers tend to be less happy with the chat box. I mean, we consider that, this could also be a sign of maybe potential skepticism of those experts, and not necessarily a better knowledge of the field or the subfield compared to the younger researchers.
Absolutely, yeah. I think it's how to. We didn't have the time to go deeper into this question. I think it's exciting I think it's a great question to answer. It's like, why is this happening? Definitely skepticism could be a part of the answer. I think maybe junior folks are a bit more forgiving with not necessarily the best answer, but they can see the potential. And maybe, I don't know, I don't want to hypothesize something that's not there, but maybe the more experienced you are, you tend to be more, I don't know, to care more about the specificity and factuality of that answer. Yeah, I think it's a great question. It would be great to explore it further again. There's so much we can do in this space, and build tools for us and you know, to cater for all different needs of the community. Yeah.
I see Alexei online has got his hand raised.
All right, yeah. Hello, so thank you very much for interesting talk. So I have a question related to such an issue, how hallucinations of all these large language models. I've done myself some experiments, but mostly in mathematics and computer science. And I got a very mixed feelings. In some sense, it just generate really plausible arguments, but easy to check that they are totally wrong. So I just wonder, in applications you have considered, how much this is an issue. For example, in astronomy or elsewhere.
Yeah, so this is something that, again, it's an anecdotal. We haven't done a study to quantify this effect, but I saw sort of an evolution of gaslighting, let's say, with this large language model. So the earlier ones, so GPT-4, GPT-4o, when I asked them a very difficult question, when I asked them a question that I knew the answer, and they were wrong, I could easily verify that they were wrong. But then with these new models like O1, O1 Pro, these more reasoning heavy models that OpenAI is coming up with, and they are kept behind the paywall. So I can access them through my grant, but they're very expensive to use. I find this sort of, I find it difficult to know if they're lying to me, if that makes sense. It takes me a lot of time to verify them. And actually, I did ask it a cosmology question. It was wrong, but this model was so convinced that it was right that by the end, I ended up giving the conversation. I just couldn't take it anymore. So yeah, so my worry, and of course, my worry for the community as well, is that as these models become more prevalent in our research and in our daily lives, and they're harder to verify, yeah, I hope that those won't propagate in the quality of our ideas and so on. But yeah, we do need to answer this question in a systematic way. It's definitely there. Yeah.
Okay, thank you.
Thank you, Alexei.
I had a question about Pathfinder.
Yeah.
So you say that astronomy is kind of relatively harmless, and I'd agree with you on that. But how people find papers and how people cite work affects people's careers directly. So at the moment, I would say humans are very good at that. You know, it's pretty common that the same papers get citations all the time. So I just wonder, how do you balance, let's say, popularity of kind of papers in a field versus what actually is most significant to the question that's asked? Because on the one hand, citation is evidence of consensus, but it also could be evidence of laziness. Can people going for the same paper again and again and again? So I wonder how much thought you've put into that and how you kind of weigh those things up.
Yeah, that's a great question. So I think your question also sort of hinges I think what we try to do with Pathfinder is not use the citations as a way to filter the papers. It's an option, of course, but it's not the underlying mechanism that allows the retrieval of these papers. So the underlying mechanism that allows the retrieval of the papers is semantic. So these papers get embedded, they get a vector, and then that vector gets compared to the question. Now, my very sort of naive thinking is that if you have a great paper that unfortunately doesn't benefit from a large resource or a large network, and this paper gets less citations than a great paper who is in a bigger group and has more citations and so on, then these two vectors shouldn't be invariably very different if they're tracing the same underlying concepts. And you can do that by semantic, by having these vectors, or you can do it in a much more guided way. And this is, again, a work that I didn't show here because I didn't have time, but Charlie and Christine, and this paper has been accepted to NeurIPS. They actually thought about identifying the concepts in that paper that are most relevant to that paper and how those concepts link to each other. And you can think about, if you have a great paper from great network and great paper from smaller network, then those concepts should also, that structure of those concepts should also be very similar. So yeah, so we are bypassing citations in a way, but we also need to spend a bit of time thinking about how to compare papers beyond the citations and what is our measure of greatness or relevance. Yeah, it's an ongoing process, I think. But my hope is that, you know, with Pathfinder, we can have something like, and this is a very simple thing that we can try, is like, say, surprise me. Just pick up a paper that didn't get a lot of citations, but is very relevant to my paper or the answer that I'm trying to get. Please bring it up. So you kind of scoop these papers from the pool, and also papers that are historical papers, people that have worked on these ideas many years ago and they get forgotten. And somehow, and I think that's not fair. And of course, you can say, hey, give me, you know, a great idea that could have been relevant to my study now from like 30, 40 years ago, by comparing with semantic or some sort of structural comparing across these concepts with mechanistic interpretability. I'm not sure if that answered your questions, but we're really thinking about it. We don't have a definitive answer yet.
Do you think tools like Pathfinder will change the way that people write papers? So just a couple of thoughts I had. The example that you showed, it seemed that the titles were very close to the question which was asked. And for what I remember from astronomy, the titles aren't always great. So is it just the risk that the people who, you know, maybe don't have any argument to being the best science, but they're the best describers of what it is that they're doing, that they kind of float to the top of the sort of the search rankings, as it were? And secondary to that, could you do you hear when people submit CVs to companies where they know there's going to be an AI looking at the CVs, they'll in a white text on the CV write a bunch of keywords because they know that, you know, the AI is just looking at the tokens, whereas the human isn't going to see it at the end of the day, so they can kind of get away with writing whatever they want. So yeah, do you think this is going to affect the way people write papers?
Oh, absolutely. I think it's definitely going to affect the way people write papers. That's beyond question. That's beyond. I would like to say, I would like it to affect writing the paper in a good way rather than in a bad way. With regards to your first question, one way we can proceed is not necessarily just look at the text, but instead have a multimodal model that also looks at the figures and looks, you know, and in that sense have an agentic AI that can run code and then, you know, not necessarily just look at the text, but also, you know, verify the mathematics by calling some mathematics module, check that the code is doing what's supposed to do by calling the coding agent, look at the figures, make sure that the figures tell the right story that, you know, as described by the text. So I do think there is a potential here to do things right with Pathfinder, just going beyond the title or the abstract or even the text. With regards to your second question, can you remind me exactly what the second question is? Because I had a thought and then I lost it.
I suppose it's, you're going to get people dumping loads of keywords and loads of sentences, which will really closely mimic the kind of things people will be searching in tools like Pathfinder.
I think that's I really think astronomers and why we do what we do goes back, in my opinion, to the dignity of our work. So I do think there will be folks that, not necessarily in astronomy, there definitely will be folks that want to, you know, use these tools to gain some sort of, I don't know, acceptance of something. But I do think that day-to-day astronomers, we deeply care about our science, we care about how we do science. I don't think our community will do that. But of course, one way to encourage the community for good practices is to, first of all, look at what kind of words these LLM-generated papers prefer. And this is actually a project that we're doing with Simon Astarita, the European Commission. He was at ESA when he started the project, and he's actually been looking at, you know, the frequency of certain words in LLM regenerated abstracts. So once the community has an idea of what are the sort of the words that these LLM generated abstracts prefer, and then if you can link that in some way to, you know, sort of an abstract acceptance rate, you can, yeah, I guess you can just tell the community, this is happening, we know this is happening, how do we want to use it? I do have trust in our community that, yeah, we will not do that. But maybe I'm wrong. I don't know. Not sure if that answers your question. But first is the quantification process. We want to see this and then sort of set the guidelines and the, yeah, let's not do this as a community because this doesn't, and maybe, yeah, then you can have like a control experiment. You can, you know, employ 5 astronomers and tell them to write 5 papers over some period of time and see, you know, how they feel about that process, how they, you know, if it helps the research, and what the community thinks about that. But for that, we need a lot of resources and funding. And yeah, it's I'm finding it harder than I thought. Yes. So yeah, thanks, Alex.
I see that Alexei's got his hand raised again.
Yeah, just if I may, very short comment on writing a papers with help of LLMs. I'm just now completing a paper and I fully thrilled and happy very much. I just asked it paragraph by paragraph, improve readability, and results I would never achieved with my non-native English. That was just perfect, exactly express my thoughts, suggesting the things. I mean, if you don't ask too much, you already get a lot, what I would say.
Absolutely, yeah, and I think also because I'm Romanian, I also struggled quite a bit with the language, and I think for the folks who come from a non-English background, this tool is really helpful. And I think it's up to our community to set the standards of what we want to do or not want to do. But I do think I think it has the potential to help as well a lot, which is why we're doing what we're doing at UTBD.
Any more thoughts from the room?
Yeah, one. Apologies if I'm keeping on for 2 minutes. I just wanted to share my humble opinion on the, on the AGI team. I mean, I'm also a supporter. I also believe the AI is revolutionizing, our understanding of the universe and astrophysics. I just wondering, do you think we should really focus, like if you had an AGI agent right now, do you think the best way of using it would actually be hypothesis generations? Wouldn't it be more useful to actually use the AGI agent to actually do the project that you create? And I'm saying so because, first of all, I've only been working for 3 years, but I've, having new ideas is not a problem, but finding time to, to actually do the project is. And also, I'd like to quote, so we had a lecture from Anna Scaife in Liverpool, and she was paraphrasing the very famous meme, this about, AI robots stealing people's job. And she was saying, I want AI to do my chores and wash my dishes so that I can focus on drawing and writing poems. So, hypothesis generation is part of the fun. Yeah, I don't know.
So what was the, sorry, I think I didn't get
the question is, wouldn't it be better to focus on building, reliable agents that can actually do the research instead of thinking about the hypothesis or something like that, like, retrieving data from surveys, plots, getting correlations, statistical testing, and that kind of things.
I think yes. So I think this is a nuanced answer, of course. So I think it's worth doing both in parallel until we can merge them together. And I think there's quite a lot of work done now on agentic AI, where you have the AI, for example, have an AI, a little AI model that reads your paper, reads your data. I have a little. I mean, at this point, I am finding it quite difficult to think about the difference between codes and agents, but generally, like, you control the agent via natural text, so it's a bit more straightforward than coding it yourself, I guess. And also you can instruct the agent, do this task for me, and then the agent has some autonomy in going and finding the information, for example, on the web and solving that task. So it's a bit more, you don't have to put in so much effort in those steps. So yeah, of course you could have that. There's actually quite a great paper from Stanford again, it's called Virtual Lab. And they actually did this they had this AI virtual lab where you had these agents interacting in a lab environment, and the human would say, hey, I want you to design this sort of protein thing for me. And the agent came up, the agent lab came in and did it for the human. And they even have an AI PI and an AI postdoc and all that. It's a really great paper. I really recommend it. But with regards to the first part, is it still worth to invest in research ideation? I do think that's the first part of the scientific discovery process is research ideation. And I can only speak from sort of an angle of democratization of science. Looking at all of these telescope proposals that, it's so hard to get telescope time on JWST, for example, or these flagship telescopes. And how do you come up with the ideas that would have a chance to compete in this very highly competitive environment? And I think that many folks, and this is completely anecdotal, I think many folks say, I don't think I could get a successful proposal. I don't have the knowledge to read all that documentation. Maybe I don't have the time. Maybe I have to teach, or maybe I come from a background where it's like, you people prefer safety over a risk for some very, very valid reason. So I think having an AI agent or an AI module that says, I'm really good at hypothesis generation, as tested through some benchmarks, and then allowing that agent to interact with the humans in an AI-human collaboration framework, and then improving the research ideation, not necessarily improving, but just assisting the human with the AI, with the research ideation process. I think that's a valid line of inquiry and of exploration, because if it works, then, you have suddenly more people, crafting their ideas better or more suited for some proposals, getting more time. There's always the question of this, these tools will be used by everyone. So how do we do this in an equitable way is still a very difficult question. But yeah, I in my opinion, I think that both lines of inquiry are valid, and we should work on both of them. As an AI scientist, like building an AI end-to-end AI astronomer, I respect those efforts quite a bit, but in my view, I do not echo the view of the rest of our team here at UniverseTBD. We have many views in UTPD, but I think my view personally is that I'd rather build an AI plus astronomer rather than an AI astronomer tool. And I think together we do need some research agent that's very good at coming up with ideas or improving or sort of augmenting human ideas, to say it in a more specific way. I'm not sure if that was a lot of fluff. I'm sorry. It's completely.
No, it's very interesting. I see your perspective. Thank you.
Yeah.
Okay, well, I was going to call it an end with that, but I can't resist asking like one little follow-up. So just you mentioned just very briefly the idea that you might be interested in an area that you want to get into, but you don't have the time to kind of commit to working on a subfield to then apply for telescope time to get the data that you would need to research properly. I guess this goes back to the idea of democratizing science and the advantages, which there are many, obviously, and also the risks of it, particularly if you're a grant funder and you hold the money and you think that either I suspect or I know that this person has written this application with the help of AI, and I'm sure they've used it very rigorously and tested their ideas and things like that. But the fact that I know that they used AI to write it or come up with some of the ideas, does that give me more or less faith in their ability to actually carry out the project were they to get the money? And then it was going to go to another question I was going to ask, which is just in terms of generic hypothesis creation. You showed the blind testing results, but if it was unblinded, do you think people would just intrinsically trust it less because it came from AI and we've all got these experiences of when ChatGPT just spouted some nonsense at us? So sorry, two questions to absolutely not finish the the seminar. Yeah.
You just have to invite me back. I mean, this is it's very good. It's good. I like it. There's like very good questions. I'm afraid that within the next 5 minutes I might not be able to honor them properly. But yeah, I think with regards to your first question, will a funder, sort of be biased? Not be biased. Will a funder tend to, if it looks at an AI, like a human that use AI to come up with a proposal, will the funder be less likely to trust that a human is, the human idea is worthy in itself, and therefore more, more willing to get the funding? I think we need to talk to the funders here. My hope is that we can set over the next few years, as all of this AI regulation is happening across the industry, we can also set some standards for science. So the paper I showed you from Stanford with 100 people doing NLP science, idea generation with NLP, they provide some guidelines at the end about that. So, you can encourage the people to disclose that they use the AI, and disclose also the ways in which they use the AI, and have some sort of like guidelines and sort of best practices or learning practices of how to use the AI, and then have a real conversation with the funding agencies that this is now the situation and the ways they would be comfortable with people using AI in their proposal. I also think that, if you ask me this question, where will be this sort of selection process in 10 years, with more and more proposals being given every year and the humans running out of time, I do need a bit more thinking time about this, but I do think the reviewing process will also see some changes in response to these advancements in artificial intelligence. Yes. With regards to your second question, it's the evaluators that we used for HypoGen knew that one of the ideas was coming from AI. So there was sort of this implicit bias that we provided. We didn't do the test where we just compared human versus human as a baseline. I think that's a great insight. We probably should think about that. But we did see a very interesting trend. Maybe I can end on this interesting trend. We're trying to write up the paper now if we find the time, but without AI, we're writing it by hand. But the trend was that when we had the HypoGen papers ideas generated in computer science, we had 5 evaluators. 3 of them were NLP researchers, like world-class NLP researchers, and the other 2 were world-class astronomy researchers that have some experience in computer science. So the expertise was very different. And what we saw was that if you ask the computer science, purely computer science experts to evaluate your ideas, you get a higher inter-annotator score. So they tend to agree a lot more with each other. Now, if you bring in the astronomy expert with computer science background, and you ask them to evaluate your idea, then the agreement drops. And evaluation is incredibly tricky, not necessarily because of blind practices, but also because of the expertise of the people doing these evaluations. And it's an open problem on how to actually evaluate things well. Definitely large language models as a judge, I can say that from the ballpark. They're not at the level where we can yet trust them, so we still need the humans in the loop, of course, but how to remove the biases or how to encourage sort of a lower bias in the human evaluators, either against AI or because of their background expertise is work in progress. It's TBD, really. But I would love to have more time to think about this. Maybe we can have another chat at some point.
Well, I think this links very nicely actually to our speaker next month, who is Simone Scardapain, calling in from the University of Rome. And his title of his talk is Explainable Artificial Intelligence for Scientific Discovery, Trends and Challenges. And I think he's coming from a particle physics perspective. So if you're interested in having well, it's not long conversations into the night because it's insanely early for you at the moment. But yeah, kind of long conversations about that next month. You'd be very welcome to come back and attend that.
Thank you so much, Alex. Yes, I will definitely want to join, of course. Thank you so much. And thank you everyone for these wonderful questions. I'm excited that the presentation elicited good questions, and yeah, thank you so much for your time as well.
Yeah, it's very early in the morning for you to be having these deep conversations. So yeah, thanks. We'll thank our speaker one last time. Yeah, thank you.
Bye. Bye.